Welcome back, students. In this video, we're going to look at mechanisms of radical reactions, specifically the arrow pushing patterns that we need to know to be successful in predicting products. In radical reactions, the arrows are very different from our regular ionic reactions that we've seen before. In radical reactions, remember that what we're going to see is the formation of singular electrons instead of pairs of electrons. What that means for us is in our radical arrow patterns, our arrow is going to look different. It's going to look like this, which is a fishhook arrow. Your fishhook arrow represents the movement of one electron. Whereas our regular arrow that had two barbs on it was the movement of two electrons. So the number of barbs on the arrows matters in organic chemistry. So make sure that you know that when we're drawing our arrows, you have to draw that fishhook arrow. Now let's look at these 6 patterns. The first pattern is homolytic bond cleavage. In this pattern, the sigma bond between two entities breaks once you have this exposed to heat or light. The type of bond that breaks when exposed to heat or light is called thermally liable, which means it breaks when it's exposed to heat or light. You'll notice that some compounds in real life are stored in brown bottles, like hydrogen peroxide, for example. Hydrogen peroxide, when you get it from the store, is stored in a brown bottle because it's really susceptible to this, and so the light from the sun will make it decompose. And there's 2 ways to draw your arrows here. You can draw it like this, or if you preferred, you can have one electron from the bond be on the top, and also we can also break from up here, right? That's just how you prefer to draw it, whatever makes you feel happy. At the end, you're going to have 2 of this radical. So the next pattern is addition to a pi bond. So this is where you already have a radical to start with. And when that radical encounters a pi bond, what it does is it reacts with that pi bond. And the arrow I'm going to draw here is going to look weird and you're not going to be happy about it. So what we'll end up with is your X bound to the carbons. So if this is carbon 1, 2, here's carbon 1, 2. All right. Now, in addition to that, we'll have a radical here. So how do we show the formation of a sigma bond between X and carbon? And that's what you're not going to like, because you're used to seeing arrows point to a pre-existing bond or to an atom. And here, your arrows are just going to meet in the middle of nowhere. And that says, form sigma bond between these 2 atoms. So I'm just going to pick a point where my arrows are going to meet in the middle of nowhere. And that's saying the X and the carbon are going to be joined together with a sigma bond. Remember that the pi bond that's breaking is made up of 2 electrons. We've drawn one arrow showing that one of those electrons forms a bond with X, while the other electron needs to go on to the carbon. I don't really like that one. I don't feel like it's specific enough. Let's go ahead and redraw that and really point to that carbon. Next, hydrogen abstraction. For hydrogen abstraction, we're going to see something similar where the hydrogen bond is going to break. One of those electrons is going to the middle of nowhere again because the halogen is going to form a bond to the hydrogen. So when you see these 2 barbed fishhook arrows meet in the middle of nowhere, the X and the H are now bound together. So these arrows are saying make sigma bond between these 2 atoms. Well, the HR bond has 2 electrons. We've only drawn where one of them is going to go. So let's draw where the other one is going to go. It's going to go on to the R group. Remember, R is our abbreviation for alkyl. So now you started with a radical, you still have a radical at the end. Instead of abstracting hydrogen, we could also abstract a halogen. So if you started with a radical, then your radical can react and pull off a halogen. And again, where these two barbed arrows are meeting, that's saying R and X are going to have a new sigma bond to one another. So these are going to have a new sigma bond, but this one needs another arrow to show what happens to that second electron in the XX bond. And it's going to go on, that should not be a multiplication symbol, let's do a plus. It's going to go on the halogen so that you have a radical for your halogen. So notice how these last three patterns, we've started with a radical and we've ended with a radical. We're going to come back to that idea at the end. All right, now let's look at elimination. In elimination reaction, what is going to happen is this is kind of like the backwards of that addition version. So you're starting with a radical where you have an X present, and what we want to end up with is an alkene and an X radical. So this bond between carbon and the halogen needs to break. One electron needs to go on to the halogen to make that halogen radical. Remember, because that bond is breaking, we need two arrows starting at that bond to show where the two different electrons go. So the other arrow is going to point to the middle of the already there sigma bond between the two carbons, because we're going to use this radical on the carbon to show that we're forming another bond between those two carbons to make that pi bond there. Right, so let's do some highlighting. This arrow and this arrow are showing the formation of the pi bond. So there's a couple of things that we're recognizing now. Right, we're seeing that if a sigma bond or if any bond is breaking, we need two arrows starting at that bond. And if we're forming a new bond, we need two arrowheads pointing to where that bond is going to form. Our last idea is called coupling. And coupling is when two radicals come together, they form a new sigma bond, and they, well, terminate, right? They end up killing the radicals. No more radicals. And that leads us into some classification of these different patterns. So let's talk about that next. There are three categories that these reactions can fall into. The initiation one was when you started with no radicals. So here's a peroxide. You add light or heat, and that bond breaks, so now you get radicals. So initiation is start with no radicals, end with a radical. Whereas termination is the opposite, right? So in termination, what happens is you start with a radical and another radical, they come together, and now you have no radicals. All of the other patterns were examples of propagation steps, where you started with a radical and you ended with a radical. For example, if we started with a R radical and we wanted to abstract a halogen, we're starting with a radical and then we're ending with an X radical. And that's the definition of a propagation step. Now, usually the order is a little bit different when you see it, because it goes when in the course of reactions, it goes initiation, where you start the radical process, propagation, where the reaction continues, and then termination is the end of the sequence. But here I just have initiation and termination next to one another to show that they're opposites of each other. Let's wrap up. In this video, we looked at the arrow pushing patterns for radical reactions, and we looked at classifying those patterns. You want to make sure that you can classify these patterns, because when we get further on and talk about something called radical polymerization, these will come up again. Thanks so much for your attention. This is Katoni signing out.